the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a second video in a series on LU factorization for matrices, and it's geared for linear algebra students who are going through matrix algebra at this moment. This video specifically is going to focus on an actual algorithm to decompose a matrix A into the product of L, a lower triangular matrix that is also invertible and square therefore, and U, a pseudo upper triangular matrix. And when I say a pseudo upper triangular matrix, it's just a matrix where everything below the pivots is zero and everything to the left of the pivots is zero. So most people would call that upper triangular. So what is the LU factorization algorithm? Well, the first thing we'll need to assume is that we're not using the elementary row operation of exchanging rows. That's going to be very, very important. Let me write that down. So beyond the fact that we have to assume that row exchanges are just not allowed, they technically can be allowed, but they end up making it difficult to derive the algorithm. So let's just go ahead and say that they can't be allowed. But the other thing that we need to have is, or need to recall, is the fact that elementary row operations on a matrix are the result of left multiplication on that matrix by elementary matrices. And I had a whole entire video on this called Elementary Matrices. And at the time I had said, these may seem like minor things like elementary matrices, because all you're doing with an elementary matrix is essentially doing a row operation on the identity matrix. So let's say you want to take 5 times row 1 and add it to row 2. Well, this is the corresponding elementary matrix for that elementary row operation. It takes 5 times row 1 and adds it to row 2. And if I multiplied A by this on the left, that elementary matrix would actually apply that row operation to A. And so at the time when we learned that in the video on elementary matrices, like I said, I mentioned at that time that that was going to be a bigger topic later on. It was worthwhile to learn at that point, but now we're really going to use that theory here. And I went ahead and wrote out what that matrix, that elementary matrix, does to the matrix A. And again, this is only through left side multiplication. Now, another thing we need to recall, elementary matrices are invertible, and this is actually super important to remember. First of all, we know from way back early on in linear algebra that every elementary row operation can be undone. And that means that every elementary matrix has something that undoes it. So if you have an elementary matrix, let's just say E sub 1, which takes row 1, multiplies it by 5 and adds it to row 2, then we know there has to exist another matrix that undoes that. And that other matrix that will undo it is called E sub 1 inverse. It brings you back to the original matrix you were playing with, which in this case we'll just say is the identity matrix. By the way, something important to notice. So if this matrix right here is E sub 1, then think about how you would undo having taken 5 times row 1 and adding it to row 2. How would you undo that operation? How would you change this element or this entry right here back into 0? Well, seems pretty obvious, maybe, that you would take negative 5 times row 1 and add it to row 2. Now it should make sense if somebody comes in the room and says, you know what I'm going to do? I'm going to take row 1, I'm going to multiply it by 5, and then I'm going to add that to row 2. And you say, I don't like that you did that. I'm going to undo that. So the way I'm going to undo that is I'm going to take negative 5 times row 1 and add it back to row 2. And that undoes your positive 5 times row 1 and adding it to row 2. And that should make sense. You can see that these are actually going to be inverse operations if you apply them to each other. The left matrix is E sub 1. The right matrix is E sub 1 inverse. If you do that multiplication, well, let's see. The first row, first column, is going to be 1. The first row, second column, well, that's going to be 0. The first row, third column, that's going to be 0 as well. By the way, if you're wondering how I'm doing it so quickly, I'm just using the dot product and I'm not really reading out what I'm doing in my head. Now we move our attention to row 2, column 1. That's going to be 5 minus 5 plus 0, which is 0. Row 2, column 2, that's going to be 1. Row 2, column 3, that's going to be 0. Row 3, column 1, that'll be 0. Row 3, column 2, that will be 0. And row 3, column 3 will be 1. That's fairly convincing, well, hopefully to you it is, that when I want to undo an elementary matrix, especially a row replacement elementary matrix, one that takes, let's say, 5 times row 1 and adds it to row 2, well, you'll take the inverse by just doing the negation of that, -5 times row 1 and adding it to row 2. All that being said, another thing we should remember, and again, this is all from the elementary matrices video, but it's good to kind of rehash it here. Since a series of elementary row operations can be performed on A to get to an echelon form, and by the way, an upper triangular matrix is an echelon form, there must exist a product of elementary matrices that you can apply via left multiplication on A to arrive at that echelon form. That is, there exists elementary matrices E1 through EP such that you perform one elementary row operation on A, then another, and so on and so forth until you're done performing all your elementary row operations to get A into echelon form. And that's an upper triangular matrix. Now we're going to combine a couple of things here. The fact that we know elementary matrices are invertible means that each of those elementary matrices that we multiplied against A have inverses. In fact, just for the moment, I'm going to call this group, this product right there, I'm just going to call that E for the moment, just to keep the notation kind of easy. And what we're going to do is multiply both sides by the inverse of E because we know that elementary matrices are invertible, and so their product is invertible as well. So that would imply that E inverse times E times A must equal E inverse times U. Now we know E inverse times E, that's the identity matrix because E and E inverse are inverses. And of course the identity matrix times A, well, that's just A. Now let me pause for a moment before I do a big reveal here, because you might already see the big reveal, honestly. Let me remind you that we are trying to take a matrix A and factor it into a lower triangular matrix, the square lower triangular matrix that's invertible actually, the product of that and an upper triangular matrix that, well, does not need to be invertible. It could be actually a non-square matrix. That's what our goal here is. And what we have done actually is we have written that we can transform A via a bunch of elementary matrices and elementary row operations into the upper triangular matrix U. And then we decided to call that collection of elementary matrices E. And then I multiplied both sides by E inverse and arrived at this picture right here. And if I want to arrive at A equals L times U, then I bet you kind of just figured out what L is. L is the inverse of all of those row operations, basically the inverse of all of those, the product of all of those elementary matrices. So another thing I want you to notice here though is that if L is equivalent to the inverse of all of those products of elementary matrices, then that tells us the products of those elementary matrices, they are going to be lower triangular, because all of the row operations that we didn't swap any rows. All of our row operations were really done by affecting things below the pivot. So all of our elementary matrices will have actions on objects below or on rows below a pivot. And so we'll end up filling this lower triangle. And therefore, all of our elementary matrices will be lower triangular matrices. And just to, again, drive that point home, you don't do any operations above because we're not doing reduced row echelon form, or we're not getting to reduced row echelon form. Instead, we're just going to an echelon form, which is the forward phase, which only involves modifying stuff below the pivots. Now, all of that being said, I've just verbally talked through how to do an LU factorization. Somebody gives us a matrix A, and we want to factor it to L times U, where U is an upper triangular matrix and L is an invertible lower triangular matrix. We have just discovered that L is the inverse of all of those row operations we used to create the upper triangular matrix. Actually, you know what? I'm going to write that down. So here I say L is the quote unquote inverse of all of the row operations we use to get to echelon form. I put quotes on that inverse because really it is the inverse of a product of elementary matrices that are representing the row operations performed on A. I just didn't want to write all that stuff out. It's actually much more understandable this way. L is just the inverse of all of the row operations we used to get the matrix A into row echelon form. And in fact, that statement right there is going to be super powerful when we start doing the actual algorithm. But let's go ahead and look at this how-to. This how-to is very short, which means we still need to figure out how to do this. Somebody gives us an M by N matrix A. Find the LU factorization. How do you do it? Well, row reduce A without using row exchanges. Okay, I could totally do that. So we're going to just get it down to an echelon form. And then we're going to track the row replacement operations, specifically their inverses. So if I add 5 times row 1 to row 2, I want to track the inverse of that. Subtract 5 times row 1 from row 2. And do that in the M by M identity matrix. Now, if you read your textbook, they might have actually a trick to doing this. I'd rather not teach the trick first. In fact, I lectured to my calculus students today about methods versus shortcuts and tricks. It is very important to learn the true method first. And the reason why is because the true method will always work. And then the tricks and shortcuts, those are fine to learn, but only after you know the actual method, because the tricks and shortcuts that you would learn in mathematics often come with caveats, like you can only use this in this one special situation or something like that. So you want to make sure that you know the true method first, and then switch gears to a trick if the trick is good enough to talk about. So for our example here, we're going to demonstrate how to get the LU factorization, and I'm going to be as theoretical as possible at first, and then we're going to redo this and it's going to speed up. But it's very important that you follow me for the theory, because the textbook that I use, which is a wonderful textbook, it actually does not describe what's happening in the background. The author just says, you just do this. And I can understand why, because the theory is a little bit tough to understand initially. So I'm going to try my best to describe the process. So first things first, we want to take A and factor it into the product of a square lower triangular matrix that's invertible times U, which is an upper triangular matrix. A is a 3x3, which tells us that L has to also be a 3x3 because it's square and its first dimension must match the first dimension of A. So there you go. So at least I know the dimension of L. Now, really, our first goal is to create U. So that's actually going to be pretty easy. So all it's going to require is for us to do our normal row reduction method. And actually, before we dive into that row reduction process, I want to take us back just one page real quickly, or maybe 2 pages actually, but I just want to remind you that L, the lower triangular matrix, is E inverse, where E is the product of all of those elementary matrices, all the elementary row operations that we're doing. And the reason why I'm saying that is because I want to convince you, if I multiply both sides of this by E, I get that the product of those elementary matrices times L should be the identity matrix. Now, you might not understand why I'm saying this, but it's for the theory part of it. Remember, those elementary matrices are these guys right here. So the same elementary row operations that are going to take A and transform it into an upper triangular matrix are exactly the same elementary row operations that would take our unfound L and transform it into the identity matrix. So what I'm going to do just for this single example is I'm going to actually find out what this matrix is, because I want to show you something very special about that matrix product of elementary matrices. And I'm going to do this by tracking all of the elementary row operations that I perform in the identity matrix at the very same time that I'm performing those elementary row operations on A. And to do that, we're going to see something that we did earlier. We're going to take A, the matrix we're working with, and we're going to place it in an augmented matrix with the identity matrix. And then we're going to row reduce A to get us to our upper triangular matrix. But when we do that, we won't have A inverse over here. So please do not think that that's going to be A inverse. Actually, what we're going to have here is the product of our first 3 elementary row operations. I say 3 because I know this problem only requires 3 elementary row operations. But if it required 10, then it would be the product of the first 10 elementary row operations. The fact is, this will give me the product of all the elementary matrices that we were supposedly multiplying both L and A by. We multiply E against L to get the identity matrix. We multiply E against A to get U, which is the upper triangular matrix. If that sounds confusing, it's actually not too bad, but it's only confusing because the authors will not do this because they don't want to really showcase this, but I think it's kind of important actually. So pretend as though you're just row reducing here. I'm going to take, let's see, row 1 and add it to row 2. I'll even track all my changes. That's actually going to be important just so I can show you something in a little bit. So 1 row 1 plus row 2, and I'll take -2 row 1 and add it to row 3. Now something, I'm going to pause for a moment and just share something here. That identity matrix that we're building, the matrix that we're building on the right-hand side that started with the identity matrix, we're slowly modifying it into a lower triangular matrix. And that lower triangular matrix, again, is going to be the product of all the elementary matrices that we used to get our matrix A into upper triangular form. But if you take a look at this, it almost looks as though we're tracking the changes that we're making right here. So we added row 1 to row 2, and look, this is a +1. And we subtracted twice row 1 from row 3, and this is a -2. Well, that pattern actually is going to break in the next step, which is why I think most authors are going to avoid this discussion. But let's just see what happens in the next step. I'm going to take 5 times row 2 and add it to row 3. And there we have it. This matrix right here is going to be U. We would have done that anyway had we done row reduction on A. So no matter what, we would have gotten to U. But what is this beast right here again? Oh yeah, that's right. It's the product of all those elementary matrices. Now remember, I'm supposed to find L here. I want A to equal L times U. We already found U, so let me go ahead and just write this as L times something. And that something is going to be the U that we have right there. There we go, I just copied it, so that's LU right there. But we don't have L yet. But what we do have is E. And remember from this page right here, E times L is the identity matrix, that is, L is E inverse. So I'd love to find the inverse of that matrix E. Now, normally you wouldn't go through all of this, so we will redo the problem in a moment, but I really, really, really want you to see something. Since L is just the inverse of E, let's go ahead and use a method that we learned in the last set of videos on invertible matrices to find the inverse of E. To do that, we would take the augmented matrix E and augment it with I, and we'd solve that. To be honest with you, we're not undoing our work before, but it will be very close to that. And this is the part I really, really, really beg you to watch. Let's start doing row reduction to where we can get eventually this to become E inverse, which will be L. Well, let's see. First thing I'm going to do take the opposite of row 1, add it to row 2, and -3 row 1 and add it to row 3. Okay, not bad. Now I'm just going to finish this off very quickly by taking -5 row 2 and adding it to row 3. Okay, great. So this is E inverse, which we've said is the lower triangular matrix. Let me write that up above, and then we're going to make a spectacular observation. Great, we have L, the lower triangular matrix, and we have U, the upper triangular matrix. Now, what about that spectacular observation that I had mentioned? Well, we didn't actually have to do all that extra work. In fact, we didn't even have to do this augmented matrix piece. All we needed to do really is do forward phase of row reduction for this matrix here and get it all the way down to U. Why do I say that? Because if you look at our row operations, we took 1 times row 1 added to row 2. What is the undoing of that? Well, it's subtracting 1 row 1 from row 2. And if you take a look at this matrix up here, subtracting one of these and adding it to row 2 would give me a -1. All right, maybe that was just by chance. Well, let's see. The next step that we did was taking -2 times row 1 and adding it to row 3. What would be the opposite of that? Adding twice row 1 to row 3. Well, if I had taken twice this row 1 and added to row 3, this would be a 2. Huh. Well, that looks kind of interesting. And finally, taking a look at our final row operation, we would have taken, or we did take, 5 times row 2 and add it to row 3. The opposite of that would be to take the opposite of 5, or -5 row 2, and add it to row 3. Well, let's see what that would have done in this matrix up here. -5 times this 1, and add it down, that becomes a -5. Now here's the deal. Notice I didn't say -5 times this as well, and this is where the authors avoid the conversation. Because if you say, oh, -5 times row 2, add it down, well then this right here should be 5 plus 2 would be 7, and that didn't seem to work out, did it? It's almost as if they skipped that, but they didn't. Because really, if all of those elementary row operations or elementary matrices times L is supposed to be the identity matrix, then L is equal to the inverse of E. Now remember, E is the product of these elementary matrices right here. E1 took 1 row 1 and added to row 2. E2 took -2 row 1 and added to row 3. And E3 took 5 row 2 and added it to row 3. But remember, there is a property of inverse matrices. If you have a product and you're taking the inverse of that product, that can be rewritten as the product of inverses in reverse order. So if I said, you know what I'm going to do? I'm going to perform the opposite of E3 first. Well, the opposite of E3 will start you at the identity matrix. E3 added 5 row 2 to row 3. So the opposite of that is going to take -5 row 2 and add it to row 3. Then we go to the next one in reverse order. And that next one, what was E2? Well, E2, we took -2 row 1 and added it to row 3. The opposite of that would be taking twice row 1 and adding it to row 3. So twice row 1, adding it to row 3. Well, twice all of this, adding it to row 3, this just becomes a 2. And then finally, the last elementary matrix. What was that operation? That operation was 1 times row 1, add that to row 2. What's the opposite of that? -1 times row 1 and adding it to row 2. Well, if you take the opposite of all of these and add it to row 2, the only thing that's going to change is this guy right here. And notice that is L. So when I say in the previous page, track the row replacement operations, specifically their inverses, in the M by M identity matrix, I really mean just by the columns. Don't multiply entire rows, just track the column changes. So what do I mean by that? Something very simple. Let's redo that problem, and this time you're going to see it in all of its full glory. All right, here's a matrix A. Find the LU factorization. All right, well, the first thing I'm going to do is row reduce A. And here's my identity matrix where I'm going to track all of my changes and watch the fun. I will take row 1, add it to row 2. So if you add those two rows, you get that right there. I'll take care of the third row as well in a moment. But what's the opposite of adding row 1 to row 2? Subtracting row 1 from row 2. Now let's go ahead and take negative twice row 1 and add it to row 3. Now what's the opposite of negative twice row 1 adding to row 3? Positive twice row 1 adding to row 3. Finally, 5 times row 2 added to row 3. What's the opposite of 5 times row 2 added to row 3? A negative 5 times row 2 added to row 3. And notice I'm not multiplying this entire row by it. I'm only affecting what's right here below this pivot. So I'll take negative 5, that's what it was, right? Yeah, negative 5 times that one and add it into that spot right there. That, folks, is L, and that is U. Something else I think is very important for you to understand, or at least see. I'm going to highlight this pivot column right before I changed it, and I'm going to highlight this pivot before I changed it. It's from the pivot downward that I'm highlighting. From the pivot downward that I'm highlighting. And I highlighted right before I changed those. If I take that row right there, or that column, and divide it by the value of the pivot, just imagine I took 3, negative 3, 6, and I divided all three elements by the value of the pivot. I would get 1, negative 1, 2. Now I go to this part of my row reduction process right before I killed below, right before I took that negative 2, multiplied by 5, and I added it down to that 10. I'll highlight that and just say, you know what? What would happen if I took that negative 2, 10, just that piece right there, and I were to divide both of them by a negative 2? So it's dividing by a negative 2. Well, the first element would turn into a 1. The second would be a negative 5. And then in this last piece, if I were to divide this by itself, because it's a pivot, negative 1 divided by negative 1 is 1. Now, I'm sure you probably want to see that in action with a bigger matrix. So let's do one final example with a huge matrix. Well, not huge, but a larger matrix. Here's the matrix we had earlier where I told you what L and U were. But this time we're actually just going to do the factorization. Notice this has 4 rows and 6 columns. So when I factor this to L and U, L will be a 4 by 4 matrix and U will be a 4 by 6 matrix. Are you ready for the fun? I'm ready for the fun. Let's do it. Here is our original matrix. I am going to highlight starting at the first pivot in that entire column. If I were to take that entire column and divide it by the value of the pivot, dividing each of these entries by a negative 2, I would get 1, 1, 2, 3. That is my first column of my lower triangular matrix. Believe it or not, it goes that quickly. Now I'm going to start my row reduction. You see how I'm doing my arithmetic here? By the way, the opposite of all those are 1, 2, 3. And if you take a look at this, 1, 2, 3. So I've already placed those in there because I had that column highlighted and divided by the pivot value. All right, let's do our arithmetic here. Negative row 1 added to row 2. Negative 2 row 1 added to row 3. And negative 3 row 1 plus row 4. Great. Now notice I have a new pivot that just showed up, this guy right here, and I'll highlight everything from that pivot down below. And I'm going to go ahead and take those values and I'm going to divide them by the value of the pivot, and that will be my next set of entries in my lower triangular matrix. 1, 2, 3. Remember, the value, it's a lower triangular matrix, so that will be a 0 up above. Let's go ahead and use that negative 1 to kill everything below. And yet another pivot has been revealed. So I'll go ahead and grab that pivot and everything below it, and I'll divide all that by the value of the pivot itself, which is 3, and I should get 1, 2. And of course, this is lower triangular, so everything above that's 0. Going back to our matrix here, one last row operation. And we have our final pivot revealed. Divide that pivot by its own value and you will get 1. We have our upper and our lower triangular matrices already factored. Now, that's how it's done, folks. That's a really nice way to do it. And I didn't mean to make it convoluted. I just wanted to showcase kind of some of the concepts behind the scenes. But really, when it comes down to it, LU factorization goes like this. Notice I'm not doing row swapping. You don't want to do row swapping. If you're faced with the possibility of having to do row swapping, then you should open your text. There might be like a little side note on what you could do if you run into that situation. And by the way, I do want to showcase that this is actually the matrix L. Remember, we had this problem earlier. So let me just hop back to right here and you can see this is the same exact matrix. So we did a good job. That's actually the same exact U as well. All right, that is the complete LU factorization method outside of row swapping. Generally, if you do have to row swap, it's usually left as an exercise to with a little bit of instruction on how to deal with that if you have to. Anyhow, I hope that you enjoyed this video. I hope that I didn't scare you away from linear algebra, and I hope you have a wonderful day. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.